as a massive earthquake strikes the Anatolian plateau. Buildings sway violently, the earth cracks open, and debris rains down from collapsing structures. Yet when the shaking stops and the dust settles, one remarkable sight emerges. A cluster of stone houses, built 9,000 years ago, still standing intact, while modern concrete buildings around them lie in ruins. These prehistoric structures, constructed without a single piece of metal or modern engineering knowledge, have survived thousands of earthquakes that would destroy most contemporary buildings. How did our ancient ancestors create earthquake-proof architecture that puts modern engineering to shame? The relationship between humans and earthquakes is as old as civilization itself. Archaeological evidence shows that some of humanity's earliest settlements were built directly in earthquake zones. Not because our ancestors were reckless, but because these geologically active regions often provided the most fertile soils, abundant water sources, and valuable mineral deposits. From the volcanic slopes of Mount Vesuvius to the fault lines of Turkey, early humans chose to build their homes in places where the earth itself was constantly moving. This choice forced our ancestors to become the world's first seismic engineers. They had to develop construction techniques that could withstand forces that modern engineers still struggle to understand. Without seismographs to measure ground motion, without computer models to simulate earthquake effects, without steel reinforcement or flexible joints, they relied on observation, experimentation, and hard-won wisdom passed down through generations of builders who lived through countless tremors. The archaeological record reveals that earthquake-resistant building techniques emerged independently in seismically active regions around the world. At Çatalhöyük in Turkey, dating to 7400 BCE, researchers discovered evidence of construction methods specifically designed to handle ground motion. The famous stone houses of this Neolithic settlement show sophisticated understanding of seismic forces and ingenious solutions that wouldn't be rediscovered until the 20th century. The key insight that ancient builders developed was that rigid structures don't survive earthquakes. Flexible ones do. This principle, now fundamental to modern seismic engineering, was discovered through bitter experience by prehistoric builders whose lives depended on creating structures that could move with the earth rather than fight against it. Archaeological evidence shows that they developed multiple techniques for creating flexible connections that allowed buildings to sway during earthquakes without collapse. At Jericho in Palestine, dating to 8000 BCE, archaeologists uncovered evidence of the world's first base isolation systems. These early earthquake engineers had discovered that buildings could be protected from ground motion by placing them on foundations that absorbed and dissipated seismic energy. The technique involved creating layers of different materials, stones, sand, and organic matter, that acted as shock absorbers between the building and the bedrock. The sophistication of these ancient base isolation systems rivals modern approaches. Analysis of foundation layers at Jericho shows that builders understood the importance of material properties in earthquake resistance. They used round river stones that could roll and shift during earthquakes, separated by layers of sand that provided damping. Organic materials like reeds and animal hair were woven into the foundation layers to provide tensile strength and flexibility. But the most remarkable discovery came from the excavation of wall construction techniques. At sites across the seismically active Eastern Mediterranean, archaeologists found evidence of flexible joint systems that allowed stone walls to move independently during earthquakes. These weren't crude constructions, but sophisticated engineering solutions that required deep understanding of structural dynamics. The technique involved creating walls from multiple independent sections, each capable of moving slightly relative to its neighbours. The joints between sections were filled with materials that could compress and expand: clay, mixed with organic fibres, sand, and sometimes even animal fat. During an earthquake, these joints would flex and absorb energy, preventing the rigid stone walls from cracking under stress. Archaeological evidence from Göbekli Tepe in Turkey, dating to 9500 BCE, reveals even more sophisticated seismic engineering. The massive stone pillars of this ancient temple complex were designed with flexible connections that allowed them to sway during earthquakes. Analysis of the pillar bases shows that they were mounted on stone rockers that permitted controlled movement in all directions. The engineering behind these rocker systems was remarkably advanced. Each pillar base was carefully shaped to create a curved interface with the foundation, allowing the massive stones to tilt and return to vertical without toppling. The curvature was calculated to provide just enough flexibility to absorb earthquake motion while maintaining structural stability under normal conditions. Tool marks on the pillar bases show that achieving these precise curves required extraordinary skill and patience. Stonemasons used carefully controlled pecking and grinding techniques to create surfaces accurate to within millimeters. The work required not just craftsmanship, but sophisticated understanding of geometric principles and structural engineering. The shock absorption systems developed by ancient builders extended beyond individual buildings to entire settlement planning. At Kyrokitia in Cyprus, dating to 7000 BCE, archaeologists discovered evidence of community-wide earthquake-resistant strategies. The settlement layout itself was designed to minimize earthquake damage through careful spacing of buildings and strategic placement of open areas. The street layout at Kyrokitia follows principles that modern seismic planners would recognize. Buildings were spaced far enough apart to prevent collapsed debris from one structure from damaging neighbors. Open areas were positioned to provide evacuation routes and emergency gathering spaces. The overall settlement design created a resilient system where earthquake damage to individual buildings wouldn't compromise the entire community's survival. Building material selection was another crucial aspect of ancient earthquake engineering. Archaeological analysis shows that prehistoric builders in seismic zones developed sophisticated understanding of how different materials behaved during earthquakes. They learned to avoid materials that became brittle under stress and favored those that maintained flexibility and strength under dynamic loading. At sites like Harsalar in Turkey, dating to 7000 BCE, researchers found evidence of composite construction techniques that combined different materials to optimize earthquake resistance. Stone provided compressive strength for foundations and lower walls, while wood offered flexibility for upper structures and roofing. The interface between materials was carefully designed to transfer loads while accommodating differential movement during earthquakes. The wood selection process was particularly sophisticated. Archaeological evidence shows that builders chose specific tree species based on their seismic properties. Oak and other hardwoods were favored for structural elements because they maintained strength under repeated stress cycles. Softer woods like pine were used for non-structural elements where flexibility was more important than strength. The joining techniques used to connect wooden elements were designed specifically for earthquake resistance. Traditional mortars and tenon joints were modified to include deliberate gaps that allowed for movement during seismic events. Wooden pins and wedges were designed to compress and expand, providing flexible connections that could absorb energy without failing. Archaeological experiments have demonstrated the effectiveness of these ancient joining techniques. Test structures built using prehistoric methods and materials have been subjected to simulated earthquake motion and performed remarkably well. The flexible joints designed by ancient builders often outperformed modern rigid connections in terms of energy absorption and structural survival. The roofing systems developed for earthquake-prone regions show particularly sophisticated engineering. At sites like Beta in Jordan, dating to 7000 BCE, archaeologists found evidence of roof designs that could flex and move during earthquakes without compromising the building's weather protection. The technique involved creating multiple independent roof sections that could shift relative to each other. These segmented roofing systems required careful engineering to maintain weather tightness while allowing for seismic movement. Overlapping sections were designed to slide past each other during earthquakes while maintaining overlap for water protection. Flexible sealing materials made from tree resins and animal fats were used to accommodate the movement while preventing water infiltration. The maintenance requirements for earthquake-resistant buildings were significant and required ongoing community commitment. Archaeological evidence shows that ancient settlements in seismic zones maintained specialized craftspeople whose primary job was monitoring and maintaining the flexible elements of earthquake-resistant structures. Joints had to be inspected regularly. Flexible materials needed periodic replacement, and foundation systems required ongoing maintenance. This maintenance knowledge was preserved through specialized training systems that ensured crucial information was passed down through generations. Master builders in earthquake-prone regions developed teaching methods that emphasized the importance of flexible construction and the techniques needed to maintain these systems over time. The social organization required for earthquake-resistant construction was complex and required community-wide cooperation. Building earthquake-resistant structures took more time and materials than conventional construction, requiring communities to make collective decisions about resource allocation and construction priorities. Archaeological evidence suggests that these decisions were made through community consensus and involved sophisticated planning processes. The knowledge systems required for earthquake engineering were encyclopedic and had to be maintained with perfect accuracy. Mistakes in seismic construction could be catastrophic, not just for individual buildings, but for entire communities. This created enormous pressure to preserve and transmit construction knowledge accurately across generations. Evidence for this knowledge preservation comes from the consistency of earthquake-resistant techniques across different sites and time periods. The same flexible joint designs, foundation systems, and material selection principles appear at sites separated by hundreds of miles and thousands of years, suggesting that effective techniques were systematically preserved and transmitted. The testing and refinement of earthquake-resistant techniques happened through the harsh teacher of actual seismic events. Archaeological evidence shows that ancient builders learned from earthquake damage and continuously refined their techniques based on observed performance. Sites that experience major earthquakes show evidence of reconstruction using improved techniques that address specific failure modes. This empirical approach to earthquake engineering was remarkably effective. Over centuries of testing and refinement, ancient builders developed construction techniques that were optimized for local seismic conditions. Each region developed its own specialized approaches based on local materials, typical earthquake characteristics, and accumulated experience. The decline of traditional earthquake-resistant construction techniques coincided with the development of more rigid building materials and construction methods. As communities grew larger and more complex, the time-intensive flexible construction methods were gradually replaced by faster, more standardized techniques that prioritize speed over seismic resistance. However, the knowledge wasn't completely lost. In many seismically active regions, traditional building techniques that incorporated earthquake-resistant principles continued to be used by indigenous communities. These traditional methods often perform better during earthquakes than modern constructions, leading to renewed interest in ancient techniques. Modern seismic engineers studying archaeological sites have gained new insights into earthquake-resistant design principles. Military engineers working in earthquake-prone regions have adapted ancient techniques for modern construction. Disaster relief organizations have incorporated traditional, flexible construction methods into emergency shelter designs. The performance of ancient earthquake-resistant buildings during modern seismic events has been remarkable. Archaeological sites that have experienced recent major earthquakes often show minimal damage to prehistoric structures, while modern buildings nearby suffer significant damage. This real-world testing has validated the effectiveness of ancient earthquake engineering techniques. Perhaps most importantly, ancient earthquake-resistant construction demonstrates that effective seismic engineering doesn't require high-tech materials or complex calculations. The fundamental principles, flexibility, energy absorption, and material selection, can be implemented using basic materials and construction techniques available to any builder. The regional variations in ancient earthquake-resistant techniques reflect different approaches to the same fundamental challenge. Mediterranean builders developed techniques optimized for the region's characteristic earthquake patterns, while builders in other seismic zones created different solutions adapted to local conditions, yet all shared the same basic understanding of flexible construction principles. The integration of earthquake resistance into overall building design was seamless in ancient construction. Unlike modern buildings where seismic systems are often added as separate components, ancient earthquake-resistant buildings incorporated seismic considerations into every aspect of design and construction. The result was buildings that were inherently earthquake-resistant rather than conventionally built structures with added seismic protection. The cost-effectiveness of ancient earthquake-resistant construction was remarkable. While these techniques required more skilled labour and specialised materials, the long-term benefits in terms of building survival and reduced reconstruction costs made them economically advantageous. Communities that invested in earthquake-resistant construction enjoyed greater stability and continuity over time. The story of ancient earthquake engineering is ultimately a testament to human adaptability and problem-solving ability. Faced with the fundamental challenge of building permanent structures in regions where the ground itself was constantly moving, our ancestors developed solutions that were not only effective, but often superior to modern approaches. When we consider the sophisticated understanding of structural dynamics, the ingenious flexible joint systems, the advanced material selection techniques, and the comprehensive community planning required for these earthquake-resistant settlements, we see not primitive builders, but accomplished seismic engineers whose innovations continue to inform modern construction practices. The next time you feel an earthquake or see modern seismic isolation systems protecting a building, remember those ancient builders who first discovered that the secret to surviving earthquakes wasn't fighting against the Earth's movement, but learning to dance with it. Their legacy lives on every time we choose flexibility over rigidity, adaptation over resistance, and wisdom over hubris in our eternal struggle to build safe homes on a moving planet.